got two curves. There's no negative here. Oh, there is negative there. There's no negative right there. Sorry about that. The first curve is negative 2 plus 10 over 1 plus x squared. So that graph actually looks something like the following. You could just graph it on the screen. But it basically looks like this. It goes up and back down. And actually hits at 10. Actually, it would hit at 10, but it's been shifted down to. So it hits at 8, actually. And then there's a y equals 12 line, which is up here. Except I just messed up. There. 9, 10, 11, 12. There we go. 7, 6, 5, 4, 3, 2, 1. Okay, there's your graph. And we're talking about between x equals negative 1, I'm sorry, x equals negative 3, and x equals positive 3. So it looks something like this. We're actually just interested in this region here. So it looks like a pair of like really cool sunglasses. Those are really cool sunglasses. If you wear those, you have cool sunglasses. All right. Now that we've established the actual definition of cooldom, we will move on to solve for the area. So this is a 7-3 concept, and I want to remind you how it works. So imagine looking at this area as a series of rectangles. This is our 7.2 idea here. Imagine taking that rectangle out and just looking closely at it. It has a width delta x, it has a height delta y. That delta y is literally the y equals 12 line minus the y equals negative 2 plus 10 over 1 plus x squared curve. So the height of that thing is 12 minus negative 2 plus 10 over 1 plus x squared. So the area of this piece is length times width. So it's basically 12 minus negative 2 plus 10 over 1 plus x squared delta x. Delta y times delta x. And then if you want to turn this into the infinite case, you know, where you have an infinite number of green rectangles, this becomes a differential. Even if you already have the answer right, just bear with me for a second here. So the differential area is the same thing with the dx. And then if we integrate both sides, we get area on the left and we get this on the right. So you basically get a on this side, and you can see that you have a 14 going on here. So the antiderivative of that is 14x. And then you have a 10 over, that's minus 10 over 1 plus x squared, but that just integrates to arctan. So you could use minus 10 arctan x, or you could use plus 10 arccot x if you want to include that negative with the antiderivative. This minus distributes, right? Okay, so you're just analyzing between negative 3 and 3. And if this was a homework problem, this would be the point in time where you realize I need a calculator, because I can't do arctan 3 without one. Sometimes you don't always know in our book, you know, when you're supposed to use a calculator. Anyway, if you type this in, you'll get the 59.019. Now this is an area, so you put square units on that. And after you realize that you were allowed to use your calculator, you might as well have just done the whole thing on the calculator. In fact, it is actually a bad idea to write the antiderivative, because if the calculator is going to do all the work, you might as well just let the calculator do all the work and not run the risk of writing something incorrectly. So suppose you had not written anything, you would have gotten the answer right. But if you wrote this and there's something wrong with it, the grader is going to feel obligated to take off points. So just leave this off. You're going straight from here. Don't forget the limits. I almost forgot. Okay? All right, any questions on part A? It's really relatively simple idea with a rectangle there. Okay, and then it gets a little bit more complicated when you talk about volume, because you're naturally dealing with a three-dimensional object. So let me show you kind of what, oops, that's a letter of rec. There we go. I was going to show you this new graph paper that I don't think you've seen before. It's called Isometric Paper, and it's used in art classes. So if you've taken art classes before, maybe you've used this sort of thing. And I'd be happy to email you a template of this. But this is pretty cool stuff, so check this out. What you do is you just draw along these lines. Has anyone ever used isometric paper before? Maybe for an art class? Okay, I gave him some, yeah. Okay, so this paper is really fun to use, and it makes everything just pop in 3D here. So we need lots of y values here. We've got to go all the way up to 12 anyway, so wish I'd been counting. Let me count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12's right there. Okay, so when you sketch your curve, the line is right here. This is the y equals 12 line. And the curve was basically that -2 plus 10 over 1 plus x squared. So I'll draw that in blue. That actually passes through -3, -1. Yeah, and +3, -1. So it looks like that. And it also passes through 0, 8. Okay, so this is supposed to look like it's lying flat on your desk, and then if you wanted to kind of sketch the desk in here to look kind of like this, this is like your desk, see? Like that. Try to follow the lines. Here's the table leg. Yeah, it really looks 3D when you do it this way. So the advantage now is when you graph your semicircles, you can actually see them standing up. So our region is bound between -3 and +3 on the x, like this. And we were planning on drawing semicircles. So I'll use green for that. Hopefully the green works. Imagine a semicircle standing up like this. Standing on the desk, standing straight up. It would be made of Play-Doh if this were last Friday, right? There are smaller ones, like the one right next to it. Looks like that. The smallest one is right there on the y-axis. That's this one here. It only has diameter 4. Some of these other ones have like diameter 13. They're bigger. So it forms this interesting solid. We don't have to sketch all of it, but you're just supposed to kind of visualize it from the side, you know. So now you can say, okay, well, what is the area of any semicircle? It's half of pi r squared, right? So the area is always 1/2 pi r squared. But it's the diameter that we know, not the radius. So we would replace the r with a d over 2. Like that. In other words, it's pi over 8 d squared. Which most people just memorize. They know, hey, if I'm going to use semicircles, the area of each one is pi over 8 d squared. Okay, so cool visual. Let's just go back now to our calculations. So for part B, you've got semicircles. The area is pi over 8 d squared. The diameter corresponds to the y2 minus y1 in your calculator, as you've got it saved probably. But basically it's just, it's the 12 minus -2 plus 10 over 1 plus x squared. That is your diameter. Okay, if you want to give that thing a little bit of thickness to make it more of a volume sort of thing, then you would need to put on a delta x. Okay, you need a delta x. And this now is a differential volume. Technically, it's a delta volume. So I went off the edge a little bit. And then you integrate both sides. Okay, so if you integrate the left side, you get volume. You can pull the pi over 8 out. If you integrate the right side, you could just type it as y2 minus y1 on your home screen. Or just type, 14 minus 10 over 1 plus x squared. And then this is quantity squared. So I would hate to do this integral by hand. because it represents like something different from just arctan now, right? Because you've squared the integrand, so we know that definitely changes everything about the calculus. So anyway, the calculator will give you the rest, and it's 247.965. This is obviously volume, so you should use cubic units. Like that. So now you realize that the only thing that would be different if we didn't use these semicircles, if we used something else, the only thing that would change at all would be this would not be a pi over 8, it would be some other coefficient. For example, if these were squares rather than half circles, then this right here would just be a 1. And if this was squares and the diagonal was resting on the plane, then this would be a 1/2. And if this was a full circle, this would be a pi over 4d squared rather than be a pi over 2d squared. Right. It would be a pi over 4d squared instead of pi over 8d squared, you see? And so I gave you that sheet, that handout on Friday. Was anyone absent? That sheet on the front had all the formulas. So semicircle pi over 8d squared, square just d squared, square on the diagonal 1/2 d squared. Okay, and now that you have those are your integrands in green here. So this saves you a lot of time, but I don't want it to reduce down to, hey, this is the formula, let's use it. I really want you to understand the cross sections and the visual side of it and the 3D look to it. So if you're interested in this graph paper, I can get you some of that. I could print it right after class, or I could just email you the template. You can print out however much you want. But I think it's kind of fun to use. Some people hate this paper, and they never use it because it's distracting to them. Okay? All right, I'm going to stop the recording, and then if there are any questions on 395, we should ask because we're turning that in. Okay?